This chapter is all about how populations evolve, how they change over time. And a big part of that is going to be this next section, which is 23.2 on what's called Hardy Weinberg equation. So I'm going to go through what that is and what that means. Because remember, we're not saying that individuals change, but populations change. And they change because of that variation. In order for evolution to happen, in other words, for a population to change in a positive way, there has to be at least one of the factors that cause evolution to be occurring. We'll talk more about what those are in a second, but first let's just talk a little bit about what a population is. So a population is a group of individuals that are capable of interbreeding and producing fertile outcome. So for example, squirrels and birds in a courtyard are two different populations, right? Because they can't breed, they cannot produce fertile offspring. The squirrels in the courtyard versus the squirrels in your backyard may or may not, depending on how you describe it, be two different populations as well. It's just kind of how wide you want to make it. But typically, a population will only interact, or I should say, only breed with its population. So here's an example of a couple of, I think these are reindeer, that overlap between the border of Alaska and Canada. And their ranges overlap some, but they tend to spend more time with their own group, either the porcupine herd or the 40-mile herd. They tend to, sometimes they'll cross over, but they're still going to interbreed primarily with just their population. Another thing we need to talk about is this concept of a gene pool. So the gene pool is in the population. It's all of the alleles in that population. So all the dominants and recessives for every gene, for every trait. Okay, that's what I'm talking about when we're talking about alleles. Remember, alleles are going to be those alternative versions of a particular gene. Like I could have eye color and I could have different colored eyes, and those would be different alleles. Or I could just have a dominant and a recessive, like a widow's peak. I either have a widow's peak or I cannot have a widow's peak. That would be two forms of the allele. When we talk about a locus, we're just talking about where that gene is located on a chromosome. So it says here, locus is fixed. It just means that it's static. It's not going to change if the individuals in a population are all homozygous for the same allele. So if everyone has the allele for a widow's peak, everyone will have an allele's peak from now until, there maybe is a mutation, right? Because everybody is homozygous for widow's peak. They all have it, so they're all homozygous. If you have more than one allele, so if you have, some people have widow's peak, some people don't. If there's heterozygous, that means that you have one copy of each. You have a dominant or recessive, or you have two copies of the allele, two different copies of the allele. Now, always for a particular trait, doesn't matter what trait it is, you're going to have two copies of the allele of the gene, two alleles, right? Who do you get one of the alleles from? From mom, and the other one is going to be from dad. So you're always going to have two alleles for a particular trait or a particular gene located in a particular place on a chromosome. So move on, come on. Now, we talk in here about dominant and we talk about recessive. When we're talking about this thing called Hardy Weinberg, we actually, instead of using dominant and recessive, we use P and we use Q. And P represents the dominant allele, and Q equals the recessive allele. All of the alleles in a population are going to add up to a value of 1 if you have them in the decimal form. For example, I could say, well, I can't really do it. because I don't know what your alleles are. Well, let's skip on to the actual example because I think that will help. So, for example, let's say I have some wildflowers, and those wildflowers they exhibit incomplete dominance. Let's talk about incomplete dominance for a second. What does that mean? Incomplete dominance.
Is it like if there was like a white cow and a brown cow,
Mhm.
it like have a child that has like these spots?
That's going to be codominance.
Red and white flowers.
Yeah, actually, just read off the screen. Yeah. So that's why we review. So incomplete dominance is where both alleles blend together, and you get a mixing, something that's halfway in between. So I could look at guinea pigs that are gray, that are black, and guinea pigs that are white. You put those two together, and you get a gray guinea pig. Okay, so the color is somewhere in between. In this case, we're talking about wildflower color. We can have red flowers, we can have white flowers, or we can have something in the middle. And if it's something in the middle, it's heterozygous because it's going to have one of the R alleles for red, and it's going to have one of the W alleles for white. We don't make either one of them lowercase because they're not dominant and recessive. They just are equal. And if they're equal, they're going to blend together. So we can figure out in this population of wildflowers that I have, let's say I have these values here of somebody went out and they counted how many wildflowers I have. Well, from that, you can then figure out how many alleles you have in the population. So now when I say alleles, what am I talking about? What would you say the alleles are for these wildflowers? There's two of them. I'll give you a hint. Yep. They're CR, or I'm just going to use R, and then there's CW, or just W. Okay. So the alleles are you either have a red allele or you have a white allele, but each individual is going to have two of those. Okay. So if I have individuals who are red, we know that they are R. Okay. So there's 320 flowers, but how many alleles are there? Because they have two alleles. 320 individuals, and they have two alleles. Okay, so here, 320 people, well, not people, flowers, and I have two alleles. Times two. Okay. So I'm going to have 640. But is that all the red alleles in this population? No. Where do we also find red alleles? In pink. Yeah. So in pink, we have another 160. That's just times one, right? Because it's not double. And that's actually shown right here. So total number of our alleles, I have 800. If I add 640 and I add 160 together, I get 800. Okay. Then the remaining, the 20 flowers, I'm also going to take that times 2. That's going to give me 40. But I also have a white allele in the pink flower. So I have an additional 160 there. So I have 200 total. Okay. So I have 800 out of a nice round 1,000 wildflowers. Poor person who had to go out there and count all these. I have 1,000, and of those 1,000, 800 are going to be red, and 200 of them are going to be white. What percentage are going to be red? 80%, right? What percentage are going to be white? 20. So the number now, it's a little different here because we're saying now we can arbitrarily say that R is P, or we can also say R is Q. It doesn't matter in this case. But we can say P equals the frequency of the R allele, which is 800, divided by the total, which is going to be 80%. Or if we keep it in a decimal, it's 0.8. Okay. And the same thing for the white. The white's going to be 200 divided by 1,000, or 20%, or 0.2. Okay. So 0.2 for one and 0.2 for the other. And look what happened to the values. So what do they add up to? They add up to 1. P plus Q equals 1. So that's how we get that value. Okay. You clapping for my Hardy Weinberg? It's very nice of you. So Hardy Weinberg, this is one of the equations, P plus Q equals 1. So obviously not, when I say there's equations in this particular section, I'm not talking about like really, really hard to understand equations. You're not going to be using any calculus, because I wouldn't be using it. They're pretty simple equations. So P plus Q equals 1 is one of them. These equations were developed with some assumptions in mind, and some really important ones. And the main assumption is that the Hardy-Weinberg equation describes a genetic makeup we expect for a population that is not evolving for a particular trait. And again, they use locus, which just means the location of the gene. But a particular trait is not changing over time. Okay, it's not changing over time. That is a yardstick. It's a way of measuring change. Because the values that you get with Hardy-Weinberg may be different from what you actually see. So I could take those wildflowers and I count them up one season, and then 5 seasons later, we've got all this weird weather going on and things are changing. And I go back and I count the number of red flowers and pink and white. And then I do the math again. And now I see maybe the P value, maybe the red allele is now 0.7 and the white one is 0.3. Okay. The values have changed from where they were 5 seasons ago or 5 years ago. That's that yardstick or measure that you can see that the population is changing and evolution is occurring. Okay. Does that make sense? Maybe? Cool. So if in a population the gametes contribute equally, let me say that again, where in a population where gametes contribute to the next generation randomly, and you have Mendelian genetics, which is what we've been talking about all along, dominant and recessive, the allele and genotype frequencies will remain the same from season to season or generation to generation in the case of the flowers. So we should see after 5 generations, if nothing's happening, if there's no evolution occurring, you should see the p-value being around 80% or 0.8 and the q being around 0.2 or 20%. When that happens, we say that the population is in equilibrium. We call it Hardy-Weinberg equilibrium. They're in equilibrium. They're not changing. They're not evolving. They're just static. Gesundheit. And that happens for some traits. But not many of them. So Hardy-Weinberg equilibrium, being in Hardy-Weinberg equilibrium, describes that the alleles stay the frequency always stays constant. And so we had our wildflowers, and they had the same population of 500 wildflowers and 100 alleles. And we have that P being a red flower being 0.8 and Q being 0.2. What that would mean was that every generation we picked out exactly 20% of the Q, the white, and we picked out 80% of the P or the red. If that happens, we can also talk about. Oops, not sure I wanted to do that. We can also talk about, now that we know P or R, and we know Q or W or white, we can calculate how likely it is for a particular genotype to show up. So we should be able to calculate, and we did it for 1,000 people, 1,000 wildflowers, but we could do it for a smaller group, or we could do it for a larger group. And we should be able to come up with the same number of individuals that have that trait as we saw in previous generations. So I could go backwards now. If I know that R is 0.8, then I know that someone who is homozygous for the R trait has one R allele, and the probability of having that is 0.8. And the probability of having a second R allele is also 0.8. So that frequency is going to be 0.64. So we can just reverse it and go back the other way around. And, if I had a different, maybe I only had 300 in the population, I could take 0.64 and I could take that times 300, and that would give me how many individuals that I should see that have red flowers. Okay? So I should be able to apply that to any population and see, oh yeah, I should see this many of this particular trait. Okay. Same thing goes for the heterozygous trait. There's a value for that too. This value we call p squared, and that represents the number that are homozygous for P. We can also look at the number that are heterozygous for P and Q. And that value we also figure out with P and Q. But we're going to multiply that times 2. And there's a reason for that, and I'm going to show you that in a second. So just hold off on that. And then the last one here is Q squared, which is going to be my 0.2. Probability of having one white allele is 0.2, and the probability of having a second white allele is also 0.2. So you multiply those together, and you get 0.04. So 4% of the population should be white, 32% should be pink, and 64% should be red. Now, we can verify that by doing a Punnett score. So we know what the frequency of having, it's kind of small. We know what the frequency of having a P or red allele is, and we know what the frequency of having a Q or a white allele is. And that is not that. That's 0.8, and that's 0.2. So if I take a flower that is heterozygous for that color, so red allele and a white allele, and then I also cross it with another flower that is also heterozygous, the red flowers are going to be two R's, and they'll end up being 0.8 times 0.8, which is 64. The white ones will be 0.2 times 0.2, and that should be your white flowers. Now, the heterozygous ones. Remember how I said the formula for calculating those was 2PQ? The reason I did that is because there's two situations where you could have a P and a Q. You can have one here, and you can have one here. So after you calculate that, you have to add those two together, or take it times 2. So it's 2pq. All right. After we do all that, we come up with another equation that also has to add up to 1. And that equation is the number of organisms that are homozygous for P, the number that are homozygous for Q, and the number that are heterozygous. And that's 2pq plus 2pq plus q squared equals 1. All got to add up to 1. Where P and Q represent the frequencies of homozygous genotypes, and 2pq is the frequency of the heterozygous genotype. So when we talk about Hardy Weinberg equilibrium, we're talking about 2 different equations that you have to look at. You either have to look at this equation, or you have to look at the P plus Q equals 1 equation. Right? Now, the nice thing is, I'm not a very mathy person, and people say, like, well, I could solve this, but if I use the quadratic equation. I'm like, what? What's the quadratic? Okay. Yeah, I don't remember that part of math. I should. My math teacher used to wear a shirt that had the quadratic equation on it. Oy. Kind of terrifying. Brings back nightmares. Anyway, you will never have to perform a quadratic equation. I'm going to show you how to do these without doing that. And there it is, just for the flower example that we have. So P squared is the CR, 2pq is the CR, and then Q squared is the CW. All right. Now, I told you that when a population is in Hardy Weinberg equilibrium for a trait, it means it's not evolving. It's not changing from season to season. That is not realistic. Populations do change. They do evolve over time. And the question, and they do that because there are things in the environment that are changing. So there are these set of principles, or tenets, or conditions, or I don't know, conditions, I call them conditions, that have to occur for a population to be in Hardy Weinberg equilibrium. In other words, for a population to not change from season 1 through season 5. So that they are exactly the same. First of all, there can be no mutations. Not once in those 5 seasons during DNA replication is there a change to the DNA. Okay, that's a big ask. Right off the bat, that's a big ask. Random mating has to occur. So in our flowers, the ones who pollinate the other ones are going to be the ones that are closer to them. Right? You're going to have, it's going to be kind of geographically distributed. The ones that are closer are going to get the pollen, and the ones that are farther away aren't going to get as much of it, or any of it. So random mating usually doesn't happen either. No natural selection occurs. That means that no critter or other factor determines which flower color survives. Maybe for some reason, the white ones are also a little more tasty, and so they get eaten before they go to seed by mice. Making that up. But point is that we know that that doesn't happen. Extremely large population. 1,000 wildflowers is not a very large population. It's pretty small. I mean, it's not obviously 10, but it's still not very, very big. And then gene flow. No gene flow. What the heck is gene flow? Gene flow basically means that populations don't change their locations over time. It could be a really windy day, and some of those seeds not only carry on to far reaches of that population, but maybe they go all the way over the mountain and now they're in a completely different valley. So they've flowed, they've moved. Okay? So point is that these are what all these have to occur or don't have to occur. I don't quite know how to say that because we got this now. All these things have to happen. There has to be no mutations, has to be random mating, has to be no natural selection, a very large population, and no gene flow for this to happen. This doesn't normally happen. So instead, we are going to see some change over generation, from generation to generation. And that is then we can say, yeah, if our numbers don't line up, it's because one of these things was affected. Either there was some selection going on, or maybe there was a mutation. Something's happening to make the population change over time and be different from where it was. So the Hardy Weinberg equation can be used to test whether or not a population is occurring, whether or not an evolution is occurring in a population. And it can also be used to determine the percentage of a population carrying a specific allele. So let's do one example, and then I'm going to we will come back to this on Monday. I want to have you a little bit of time to let this kind of process in your head by, not paying any attention to it over the weekend, because I feel like that helps to kind of solidify things. And then when we come back on Monday, I'm going to give you some practice problems to do. But I'm not going to do that now because you got enough work going on. And I think it's better if you wait a few days or overnight at least. So there is this disorder that is called fetal ketonuria, or PKU for short. And this is the inability to digest the amino acid phenylalanine. And it's usually it's discovered hopefully early on in infancy, that children can't digest this amino acid. And what can happen is if they have a diet that's high in that substance, in that amino acid, it can cause permanent brain damage. So you have to be very careful about what you feed infants, and milk products would be one of those. So you have to really be careful with what you're giving your child. So fetal PKU is a recessive trait. You need 2 of the recessive alleles to get it. And in our population in the world, the gene does not mutate very well, or doesn't mutate very often, so it has a low mutation rate. And believe it or not, selection or mating is kind of random, because you don't go up to a person typically and say to them, do you know if you have the gene for PKU? Because if you are, we can't have children together, right? That's not a thing. So no one even usually knows, right, if they're a carrier for it. That's just something that people don't know about, don't ask about. So that's going to be random in terms of the selection. What was the number? Oh, natural selection. Natural selection can only act on rare homozygous individuals who do not follow dietary restrictions. So most kids, it's figured out really early, and you are careful with your diet, and so kids aren't there's no natural selection, in other words, because we've figured it out. We can keep these kids from getting sick from it, from having brain damage from it, and they can live nice, healthy, happy lives. So there's really not any natural selection. The population is large. We're talking about, the entire world, basically. Migration has really no effect. You can move from one place to another, because if you go from population to population, the frequency of PKU is pretty much the same, or I should say the frequency of having that recessive allele is pretty much the same. So this is an example of a population that would be in Hardy Weinberg equilibrium for this particular a trait. Right? So we can then figure out, if we know how many people get PKU, then we can figure out how many people in the population are carriers for it. So we start off with the known fact that PKU occurs in about 1 in every 10,000 babies born. Okay. That gives us that tells us how many people are born. Yep. Let me clear that out. That doesn't look very good. Well, I guess it doesn't look too bad. All right, that's supposed to be a Q. How's that? That are born QQ. They're born with two small recessive alleles, or they're born QQ. So if I take that and I plug that into my calculator, I just move my decimal point over, that gives me a frequency of people who have the condition is 0.0001. All I did was take 1 and divide it by 10,000. And I can also figure out how many people have the allele, because this is Q squared. How can I find Q? Take the square root of it. Yeah. So all I do is I take the square root of this value and plug that into my computer, and it gives me 0.01. Now I know Q. I know how many people are carrying that recessive allele in the entire world, basically. Well, actually, this is the U.S., so we'll just keep it with U.S. In the U.S. So what percent is that? 1%. Not that you need to know that right now. So, but if 0.01% of the population have the recessive allele, how many don't have it? How many? Sorry, I shouldn't say that. That was the wrong way to say that. How many people in the population must have the dominant allele that does not have it? 99. Okay. So, and all I did was I'm going to use this equation, P plus Q equals 1. And I know Q. So if I take 1 minus Q, it will give me P. So I know that 99% or 0.99 of the population don't have that allele. All right, sorry, let me say that one more time. That have a dominant allele. They have the dominant allele. But now I want to know how many people are carriers. Now I want to go back, and I'd like to figure out how many people are going to have that are going to be a carrier. They're going to have that allele, but they're not going to show it. So then I can take my other equation, which is P squared plus 2PQ plus Q squared. What does P squared represent in this problem? What population of people? Not carriers. So this is people who do not have a recessive allele for PKU. They're homozygous dominant. What about Q squared? We figured that one out already. That's the people who have 2 copies of the recessive allele, so they're showing the PKU trait. This 2PQ, this represents the number of people who have 1 dominant allele and 1 recessive allele. So I take 2, and I take it times my P value, and I take it times my Q value, and I get this value here. 0.0198. And that is about, if I take that times 100, right? That's about 2% of the population that are carriers for it. So you can, when you have a trait like this, you can work backwards and you can figure out how many people in the population must be a carrier for the trait. Okay. Now I won't give this to you now because I know you don't want it and I don't want to give it. But we're going to do a little example with some dragons. We'll do that next week. And you'll get to play with dragons, not really. You'll have a worksheet where there'll be some dragons that you're going to be trying to figure out different traits for.